Late March, 1943. Kummersdorf Proving Ground, Brandenburg, Germany. The morning sun cast long shadows across the testing facility as three Wehrmacht mechanics stood before a freshly delivered M4A1 Sherman tank, serial number USA 3042916. The vehicle still bore traces of North African sand in its track links and the faint outline of an American star beneath hastily applied German markings. What began as routine technical inspection would end with a realization that shattered every assumption these men held about industrial warfare. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. This single captured tank, one among thousands produced by American factories, would force German engineers to confront an uncomfortable truth. The United States had not simply built more tanks, they had fundamentally reimagined what tank production meant, achieving manufacturing velocities that German industry, for all its vaunted engineering excellence, could not comprehend, much less match. The mathematics were brutal. 40,000 Sherman tanks built in roughly 2 years. The entire calculation defied everything German military planners understood about armored vehicle production. Chief Mechanic Franz Weber circled the Sherman slowly, notebook in hand. Beside him stood Otto Richter, a transmission specialist with 15 years' experience maintaining Panzerkampfwagen models, and Heinrich Baumann, an engine technician who had worked on everything from civilian trucks to the massive Maybach power plants in Tiger tanks. Their assignment was straightforward. Disassemble this American tank, document every component, determine how it was manufactured, and most importantly, understand how the Americans could possibly produce these vehicles at the reported scale. German intelligence estimates suggested American factories were delivering between 1,500 and 2,000 medium tanks monthly. The numbers seemed impossible. Germany's entire tank production across all manufacturers, all models, and all facilities barely exceeded 350 vehicles per month. Even accounting for American industrial superiority, the reported production figures suggested capabilities beyond what German engineers believed physically possible. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Weber opened the engine compartment first. The Continental R975 radial engine sat cleanly mounted, its 9 cylinders arranged in a circular pattern characteristic of aircraft power plants. This wasn't sophisticated technology. Radial engines had powered American aircraft since the 1920s. The design was mature, proven, and most significantly, already in mass production for aviation applications. Richter immediately noted the implications. They used an existing engine. They didn't design something new. They adapted something they were already making by the thousands. This is automotive thinking, not military thinking. Baumann examined the installation more closely. The engine mounts were simple fabricated steel brackets, nothing exotic. The cooling system used standard automotive radiator technology. The air filtration employed conventional elements similar to truck designs. Every component reflected a philosophy of using proven, available parts rather than developing specialized military equipment. Weber photographed the engine from multiple angles while making detailed notes. Engine mounting requires no specialized tooling. Standard industrial fasteners throughout. Air intake design allows rapid filter replacement. Oil system accessible for maintenance. Nothing here requires craftsman skills or specialized facilities. The transmission examination revealed even more significant insights. German tank. Transmissions represented some of the most complex mechanical assemblies their industry produced. The Panther tank's AK 7200 transmission required precision-cut gears, intricate synchronization mechanisms, and skilled craftsmen to assemble and adjust. Each unit took experienced technicians several days to build. The Sherman's transmission was fundamentally different in conception and execution. Richter removed the transmission cover and immediately called his colleagues over. "Gentlemen, you need to see this. The Americans are using automotive components. This isn't a military transmission. It's a truck transmission scaled up for the load. The internal examination confirmed his assessment. The transmission featured 5 forward speeds with synchronized shifting in 2nd through 5th gears. Synchronizers, standard in American automobiles since the mid-1930s, eliminated the need for double clutching and allowed ordinary drivers to operate the vehicle with minimal training. German tanks required extensively trained drivers who mastered complex clutching techniques and precise throttle control. The Americans had designed their tank transmission for conscript soldiers with basic driving knowledge. Weber understood the production implications immediately. Synchronizers mean standard automotive machining. The gear cutting is straightforward. The assembly doesn't require precision adjustment. A reasonably equipped machine shop could make these transmissions using normal automotive manufacturing processes. They're not building custom military equipment. They're scaling up civilian automotive production. The differential and final drives reinforced this pattern. Where German designs employed straight-cut gears requiring precise tolerances and frequent maintenance, the Sherman used helical-cut gears that distributed stress across multiple teeth simultaneously. This design standard in American automotive manufacturing provided exceptional durability with forgiving tolerances. Baumann examined the gear teeth under magnification. These gears have generous tolerances. The machining quality is good but not exceptional. They're relying on design robustness rather than manufacturing precision. This is how you achieve high production rates. You design components that work reliably even with acceptable variation in manufacturing quality. The suspension system examination continued the pattern of automotive rather than military thinking. The Sherman employed vertical volute spring suspension, a simple and robust design that used large coil springs enclosed in cylindrical housings. Each road wheel pair connected to a spring unit that absorbed shock through compression of the coil. German tanks typically used torsion bar suspension, technically superior in many performance metrics, but requiring complex installation and specialized metallurgy. The American system was cruder but dramatically simpler to manufacture and maintain. Weber documented the suspension mounting points. Each spring unit bolts to the hull using standard industrial fasteners. The entire suspension assembly could be manufactured by any facility capable of basic metalworking and heavy spring production. They've chosen simplicity over sophistication everywhere we look. Richter pulled out production estimates he had brought from the Warproof 6, the German Army Ordnance Office responsible for tank development. Our intelligence suggests they're producing 40 to 50,000 Sherman tanks. If these numbers are remotely accurate, it means they're delivering approximately 1,000 tanks per month, sustained over multiple years. He paused, looking at the disassembled components spread before them. Based on what we're seeing here, I'm starting to believe those numbers might be real. The metallurgical examination provided further insights into American production methods. German tank armor employed face-hardened steel, heat-treated to provide maximum hardness on the outer surface while maintaining toughness in the core. This process required sophisticated furnaces, precise temperature control, and skilled metallurgists to execute consistently. The Sherman's armor was different. Baumann examined core samples from armor plates, measuring hardness at various depths. This is homogeneous rolled armor, same hardness throughout the thickness, much simpler to produce. You're rolling standard alloy steel plate and cutting it to size. No heat treatment beyond basic stress relief. Any steel mill with heavy rolling equipment can manufacture this armor. Weber considered the implications. Simpler armor means they can source from multiple suppliers. They're not dependent on specialized facilities. They can scale production horizontally by bringing more steel mills online. The welded hull construction amplified these advantages. German tanks primarily used riveted armor assembly, a labor-intensive process requiring skilled workers to drill precise holes and install thousands of rivets per vehicle. The Sherman hull was fully welded using production jigs and fixtures. Richter examined the weld seams closely. These are good production welds. Not beautiful, but entirely adequate. Consistent penetration, minimal defects. They're using welding fixtures to position the plates accurately. Then, standard arc welding techniques to join them. The critical insight is that welding is faster than riveting and requires less specialized skill. Train someone for 2 weeks on production welding, and they can make acceptable welds. Train someone for 2 weeks on precision riveting, and they're barely competent. Baumann pointed to the hull floor. Notice they're using flat plates wherever possible. Minimal complex curves or compound angles. This simplifies both the cutting and welding processes. They've designed the hull geometry for manufacturing efficiency. The turret examination continued, revealing American production philosophy. The turret casting was a single piece, poured molten steel into a large mold and machined to final dimensions after cooling. German turrets typically used welded plate construction, assembled from multiple armor pieces. The American approach was audacious. Casting required enormous foundry facilities capable of handling extremely large molds, but once the foundry infrastructure existed, production could proceed rapidly. Weber studied the casting quality. This is impressive foundry work. A casting this size requires sophisticated mold making and pouring techniques. But the genius is that once you've perfected the mold and the process, you can produce turrets quickly and consistently. There's no assembly time, no welding, no riveting. Just pour, cool, extract, and machine. Richter checked his notes. Our intelligence indicates they have multiple facilities producing these castings. If each facility can produce several turrets per day, the production numbers start making sense. The tracks represented another revelation in design philosophy. The Sherman used rubberized tracks with rubber blocks bonded to steel shoes. This provided better ride quality and longer component life compared to all steel tracks. Baumann examined the track construction. These rubber blocks are vulcanized to the steel. This isn't sophisticated. It's standard rubber manufacturing. The Americans have enormous rubber production capacity from their automotive tire industry. They simply applied existing rubber technology to tank tracks. Weber measured the track pin design, standard pins, standard bushings, standard lubricants. Nothing here requires specialized components or manufacturing processes. They could make these tracks at any facility that handles steel fabrication and rubber molding. The Americans are leveraging their massive automotive supply base. The gun mount and fire control systems showed similar patterns of practical simplicity. The 75mm gun mounted in a simple cradle with manual traverse and elevation controls. The gunner operated the weapon using mechanical linkages and optical sights that, while effective, employed no exotic technologies. Richter examined the gun mounting. This is basic mechanical engineering executed well: gears, pinions, and manual cranks. The Americans didn't try to create a sophisticated stabilization system or powered traverse. They built something that works reliably, using components any machine shop can produce. Weber checked the ammunition storage. The rounds are stored in ready racks with simple spring-loaded retention. Easy to load, easy to remove. They've designed everything around operational use by ordinary soldiers with limited training. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. The electrical system examination reinforced the automotive approach. The Sherman used a 24-volt system with standard commercial generators, batteries, and wiring. German tanks employed increasingly complex electrical systems with specialized components that required expert maintenance. Baumann traced the wiring harness. This is simplified to an extreme. Minimal wiring runs, standard gauge wire, conventional connectors. They've reduced the electrical system to essential functions only: engine starting, lighting, and basic instruments. Nothing exotic. Weber pulled the radio installation and examined the mounting. The radio is a standardized military set, but the installation uses commercial automotive mounting techniques: rubber vibration isolation, simple brackets, accessible for maintenance. Everything designed for rapid installation during assembly. By mid-afternoon, the three mechanics had completed their initial examination and documented hundreds of observations. They gathered in the facility workshop to compile their findings before drafting the preliminary technical report. Richter spread his notes across the server, a workbench. The pattern is unmistakable across every system we examined. The Americans have systematically chosen automotive components and manufacturing methods over specialized military hardware. Weber nodded. More significant is what this tells us about their production capacity. They're not building these tanks in specialized military arsenals. They're building them in converted automobile factories using existing supply chains and workforce skills. Baumann added his assessment. The genius is in the system-level thinking. Each component is simple enough that multiple suppliers can manufacture it. The assembly doesn't require highly skilled craftsmen. The design tolerates manufacturing variation, and the entire vehicle can be maintained by mechanics with standard automotive training. This isn't just a tank design, it's a production system design. Weber began drafting the report's key conclusion. Our technical examination of captured American tank serial number USA 3042916 reveals that reported American production figures of 40,000 plus Sherman tanks in approximately 2 years are not only plausible, but are directly enabled by their fundamental design philosophy. The Americans have treated tank production as an automotive manufacturing problem rather than a specialized military production challenge. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The implications became darker as the mechanics continued their analysis. Richter calculated production requirements for a single German Panther tank. Our current Panther production requires approximately 300,000 man-hours per vehicle when we account for all subcomponent manufacturing. At peak efficiency, we're producing approximately 150 Panthers monthly across all facilities. He compared this to the Sherman data before them. If the Americans have achieved even half the efficiency that their design suggests possible, they could be producing Sherman tanks with perhaps 100,000 man-hours per vehicle or less. At that rate, their reported monthly production of 1,500 to 2,000 tanks becomes entirely believable. Weber understood the strategic calculation. We're producing roughly 350 tanks monthly total across all models. If American reports are accurate, they're producing 5 to 6 times our total output in Sherman tanks alone, and they're simultaneously producing tank destroyers, self-propelled artillery, and other armored vehicles. The industrial disparity is overwhelming. Baumann examined the Sherman components laid out in the workshop. Everything we're seeing suggests they've optimized for production velocity and volume. They've accepted trade-offs in technical sophistication to achieve manufacturing efficiency. It's the opposite of our approach. We pursue engineering excellence in individual vehicles. They pursue industrial excellence in volume production. The final section of their preliminary report documented the most troubling conclusion. Weber wrote carefully, choosing words that would be understood by senior Wehrmacht officers. The American M4A1 Sherman tank represents a fundamentally different approach to armored vehicle design and production. Where German practice emphasizes technical sophistication, specialized components, and highly trained manufacturing personnel, American practice emphasizes simplified design, automotive-derived components, and production methods enabling rapid volume manufacturing using semi-skilled labor. He continued. The implication for comparative industrial capacity is severe. American production estimates, suggesting 40,000 plus Sherman tanks in approximately 2 years, appear consistent with the manufacturing philosophy evident in this vehicle's design and construction. German industry, organized around craft traditions and specialized military production facilities, cannot match this production velocity regardless of engineering skill or worker dedication. Richter added a technical addendum to the report. Our examination suggests that American tank production benefits from decades of automotive industry development. Component standardization, precision machine tools, production line assembly, and integrated supply networks developed for civilian automobile manufacturing have been directly applied to military vehicle production. Germany lacks equivalent automotive industry maturity and cannot rapidly develop comparable capabilities during wartime. The three mechanics worked into the evening, completing detailed photographs, measurements, and component sketches. Their report would ultimately run to 73 pages with extensive technical appendices, but the core conclusion required only a single sentence. The Americans have industrialized warfare itself, and we cannot compete at their scale. April 1943, Wehrmacht High Command, Berlin. The report from Kummersdorf arrived in a leather portfolio marked with the highest classification level. General der Panzertruppen Heinz Guderian, Inspector General of Armored Troops, read the document twice before calling a meeting of senior tank development officials. The conference room gathering included representatives from Wahrproof 6, the Army Ordnance Office, officials from major tank manufacturers including Krupp, Daimler-Benz, and MAN, and senior Wehrmacht logistics officers. Guderian opened the meeting with characteristic directness. "Gentlemen, we have received a comprehensive technical analysis of a captured American Sherman tank. The findings confirm our worst strategic fears regarding relative industrial capacity." He distributed copies of the executive summary. "The Americans are not building better tanks than we produce. They are building adequate tanks in quantities we cannot match." The German officers reviewed the summary in silence. The production estimate seemed impossible to credit. 40,000 Sherman tanks in roughly 2 years represented manufacturing velocities that exceeded Germany's entire tank production by a factor of 5 or more. An ordnance official spoke first. "These production figures must be exaggerated. American industrial capacity is substantial, but producing tanks at this rate would require hundreds of facilities and hundreds of thousands of workers." Guderian responded grimly. "Our mechanics examined one vehicle in exhaustive detail. Their conclusion is that everything about the Sherman's design enables rapid mass production using automotive methods. If they are correct, then the reported American production numbers are entirely plausible." A representative from Krupp raised the fundamental question: can we adopt similar production methods? Can we simplify our designs and increase our output to competitive levels? The silence that followed answered the question before anyone spoke. A logistics officer finally responded: "Our production system is fundamentally different. German tank manufacturing relies on specialized facilities, highly skilled craftsmen, and custom component fabrication. We have neither the machine tools, nor the factory space, nor the workforce training to implement American-style automotive production methods," he continued. "Moreover, our tanks have become increasingly complex as we pursue technical advantages. The Panther requires more specialized components than the Mark IV. The Tiger requires even more. We are moving in the opposite direction from the Americans. We are reducing production volume in pursuit of individual vehicle superiority." Guderian understood the implications completely. The Americans have solved the fundamental problem of industrial warfare. They produce adequate weapons in overwhelming quantities. We produce superior weapons in insufficient quantities. In a war of attrition, their approach defeats ours, because superior technology cannot overcome numerical impossibility. The meeting concluded with no actionable decisions. German industry could not fundamentally restructure its production methods during wartime. The specialized facilities, skilled workforce, and complex supply chains serving current production could not be replaced with automotive-style manufacturing without crippling existing output during the transition. The strategic calculation was brutally simple. Germany would continue producing technically sophisticated tanks in limited numbers because no alternative approach was feasible. The Americans would continue producing simplified tanks in overwhelming numbers because their industrial system enabled this approach. The mathematics of industrial capacity would determine the war's outcome as surely as any battle. Summer 1943. Detroit Tank Arsenal, Warren, Michigan. While German mechanics in Brandenburg documented their troubling discoveries about Sherman tank design philosophy, American production lines were validating every conclusion those mechanics had reached. The facility operated continuously across 3 shifts, 7 days per week. Finished Sherman tanks rolled off the final assembly line every 55 minutes at peak production. The factory floor stretched across 113 acres of connected buildings. Raw steel entered at one end, finished tanks departed at the other. In between, 35,000 workers executed precisely choreographed manufacturing operations that transformed automotive components into armored fighting vehicles at industrial velocities that would have seemed impossible just 3 years earlier. The production system embodied everything German mechanics had theorized when examining the captured Sherman at Kummersdorf: standardized components from multiple suppliers, simplified assembly sequences requiring minimal specialized skills, automotive manufacturing techniques applied to military equipment, and most significantly, production velocity that made quantity itself a weapon system. Each major Sherman component followed dedicated production lines, feeding the main assembly sequence. The hull line welded armor plates using production jigs that positioned components precisely, allowing semi-skilled welders to create structurally sound assemblies after minimal training. The turret line received castings from multiple foundries, machined them to specification, and installed gun mounts and fire control equipment. The powertrain line assembled engines, transmissions, and final drives using components sourced from dozens of suppliers across American automotive industry. The genius of the system lay not in any single innovation, but in the systematic application of proven automotive manufacturing principles to military production. Highland Park had been mass-producing automobiles since 1913. River Rouge had refined continuous flow production through the 1920s and 30s. Detroit Tank Arsenal simply extended these mature industrial methods to a new product category. Workers installing transmission assemblies required 2 weeks of training to achieve acceptable productivity. The transmission itself, built by suppliers using automotive machine tools and manufacturing processes, arrived pre-assembled and tested. Installation consisted of positioning the unit, bolting it to the engine, and connecting the drive shaft. No adjustment, no custom fitting, no specialized expertise beyond basic mechanical aptitude. This approach repeated across every assembly station. The suspension installation team bolted pre-assembled vertical volute spring units to standardized mounting points. The track installation team connected pre-assembled track sections using standard pins. The electrical team routed prefabricated wiring harnesses through predetermined paths. Each operation had been simplified to the minimum complexity necessary to achieve functional results. 2. Production velocity achieved by mid-1943 would have seemed fantastical to traditional military arsenals. Detroit Tank Arsenal alone produced more than 14,000 tanks between 1942 and 1945. When combined with production from Chrysler Corporation, Fisher Tank Division, Federal Machine and Welder Company, Pacific Car and Foundry, and other facilities, total Sherman production exceeded 49,000 vehicles. These numbers represented more than impressive industrial statistics. They embodied strategic advantage that no amount of technical sophistication could overcome. German Panthers might have superior guns and better armor protection. German Tigers might dominate individual tank engagements, but German industry could not produce these vehicles in quantities sufficient to counter American numerical superiority. The mathematics remained brutally simple throughout the war. American factories delivered Sherman tanks faster than combat consumed them. German factories delivered advanced tanks slower than attrition eliminated them. Industrial capacity determined operational capability, which determined strategic outcomes. Fall 1943, Kummersdorf Proving Ground. The German mechanics who had examined the captured Sherman months earlier received new assignments. Additional Sherman tanks had been captured in Italy and North Africa. Each vehicle required examination, documentation, and analysis to understand American production evolution and identify potential weaknesses. Weber, Richter, and Baumann approached each new examination knowing what they would find. Incremental improvements in specific components. Minor design changes addressing field feedback. Continuous refinement of proven designs rather than revolutionary alterations. The American approach remained consistent across all vehicles examined. Reliable automotive engineering applied systematically to military requirements. One Sherman captured in Sicily bore evidence of combat damage and field repairs. Baumann examined the repair work closely. Look at this. They replaced the damaged transmission with a new unit. The swap was completed in the field with standard tools. No specialized equipment, no precision adjustment, no expert technicians required. This is maintenance designed into the system itself. Weber documented the observation. German tanks required depot-level maintenance for major component replacement. Transmissions, engines, and final drives needed specialized facilities, trained technicians, and often custom fabrication to restore vehicles to operational status. The Americans had designed their tank for field maintenance using component replacement rather than repair. Failed parts were swapped out. Replacement parts were standardized and interchangeable. Field maintenance kept vehicles operational with minimal downtime. Richter understood the strategic implication. They're treating tanks like trucks. When something breaks, you replace the broken component and continue operating. You don't need skilled mechanics. You need adequate spare parts and standard tools. This approach requires enormous industrial capacity to produce spare components, but they clearly have that capacity. Another captured Sherman provided evidence of production improvements. The welding quality was notably better than earlier vehicles. Component finishing showed enhanced attention to detail. Small design changes addressed known weak points in earlier models. Baumann noted each improvement in his technical diary. They're learning from field experience and implementing changes across their production system. This is continuous improvement at industrial scale. Weber calculated the implications. If they're producing 1,500 to 2,000 tanks monthly and simultaneously implementing design improvements, they have feedback systems and engineering resources we cannot match. They're not just building tanks. They're evolving the design in real time based on combat data. The German mechanics compiled their findings into quarterly reports submitted to Wehrmacht High Command. Each report documented American production sophistication and concluded with increasingly pessimistic strategic assessments. The Americans had not simply outproduced German industry, they had created a self-improving production system that learned from experience and continuously enhanced capability. Winter, 1943 into 1944. The industrial war's mathematics became undeniable. American Sherman production exceeded 50,000 vehicles when accounting for all variants. German tank production across all types totaled approximately 27,000 vehicles through the entire war. The disparity in medium tank production was even more stark. Germany produced roughly 6,000 Panther tanks and fewer than 1,500 Tiger tanks, both supposedly superior to Sherman's in technical specifications. But technical superiority, measured in individual engagement outcomes, meant nothing against overwhelming numerical superiority derived from industrial capacity. German tank crews might achieve favorable kill ratios in isolated battles. American tank units could absorb losses and continue operations because replacement vehicles arrived faster than combat consumed them. The captured Sherman at Kummersdorf, that single vehicle designated FGS-2 259, remained at the proving ground through 1944. German engineers conducted repeated tests, measuring reliability, documenting maintenance requirements, and analyzing every aspect of American design philosophy. The vehicle accumulated thousands of test kilometers without major mechanical failure. The engine maintained consistent performance. The transmission shifted smoothly. The suspension absorbed punishment without structural damage. Each test run reinforced conclusions German mechanics had reached in their initial examination. The Americans had built a tank that worked reliably under conditions that defeated German equipment. They had achieved this through systematic application of automotive engineering principles rather than pursuit of technical sophistication. And they had done so at production scales that German industry, despite its engineering excellence, could not approach. Weber wrote in his final report on the Sherman examinations, dated February 1944, After 18 months of comprehensive testing and analysis of multiple captured American M4 tanks, we conclude that these vehicles represent a fundamentally different approach to military vehicle design and production. The American philosophy prioritizes manufacturing efficiency, operational reliability, and ease of maintenance over technical sophistication or superior performance in individual specifications. This approach, when combined with American industrial capacity, produces strategic advantages that cannot be overcome through engineering excellence alone. Germany lacks both the industrial infrastructure and the remaining time to adopt comparable production methods. The outcome of armored warfare in this conflict will be determined by American industrial superiority, regardless of German technical achievements in tank design. The report circulated through Wehrmacht High Command and reached senior Nazi leadership. No policy changes resulted. German industry continued producing technically sophisticated tanks in limited quantities because no alternative remained feasible. The Panthers and Tigers and King Tigers that rolled from German factories represented engineering excellence applied to losing strategic calculations. Spring 1945. As Allied armies advanced through Germany from both west and east, the accumulated evidence of industrial disparity became visible in every combat zone. Abandoned German tanks lined roads, victims of mechanical failure as often as enemy fire. American Shermans continued operating, supplied by logistics systems that delivered fuel, ammunition, and spare parts with automotive industry efficiency. The final accounting was devastating for German military planners who had believed technical superiority could overcome material disadvantages. American industry had produced 49,234 Sherman tanks of all variants. This represented more medium tanks than Germany produced tanks of all types combined. The production was achieved in roughly 4 years, using workforce that included women, recent immigrants, and workers with minimal manufacturing experience before the war. German industry, employing highly skilled craftsmen and operating specialized military production facilities, had produced approximately 27,000 tanks of all types across 6 years of war. The disparity was not explained by worker dedication or engineering knowledge. German craftsmen were highly skilled. German engineers were technically excellent. The disparity resulted from fundamental differences in production philosophy and industrial organization. The Americans had treated tank production as an industrial engineering problem and solved it using automotive manufacturing methods. The Germans had treated tank production as specialized military manufacturing and pursued technical excellence over production efficiency. Both approaches were internally consistent and professionally executed, but in total war requiring sustained mass production of reliable equipment, the American approach proved decisively superior. Post-war analysis by military historians and industrial economists confirmed conclusions that German mechanics at Kummersdorf had documented as early as mid-1943. The Sherman tank had not won battles through superior firepower or armor protection. It had won through superior logistics, sustained availability, and overwhelming numerical presence derived from American industrial capacity. Every Sherman that reached the battlefield represented not just 30 tons of steel and machinery, but the accumulated power of American automotive industry maturity, decades of production line development, integrated supply networks connecting thousands of manufacturers, and systematic engineering approaches that prioritized practical functionality over theoretical optimization. The tank was the physical manifestation of industrial advantage that decided the war's outcome as surely as any military campaign. The captured Sherman at Kummersdorf, examined so exhaustively by Weber, Richter, and Baumann in 1943, survived the war. Soviet forces captured the proving ground in April 1945 and found the American tank among other test vehicles. The Soviets, themselves operating on automotive production principles similar to American approaches, recognized the Sherman's significance immediately. They documented the vehicle and incorporated lessons learned about mass production into their own tank development programs. The legacy of that single examined Sherman extended far beyond its physical existence. The German mechanics' reports documenting American production philosophy influenced post-war German industrial development. When West Germany began rearming in the 1950s, tank designers consciously adopted reliability and maintainability principles they had observed in American vehicles. The Leopard tank program, beginning in the late 1950s, explicitly prioritized operational availability and ease of maintenance over pure performance specifications. The lessons applied more broadly across military-industrial planning. Modern defense procurement emphasizes production feasibility, supply chain integration, and life cycle maintenance costs alongside technical performance. These considerations, routine in contemporary military planning, were learned through painful experience during World War II, when German technical sophistication repeatedly failed to overcome American industrial maturity. The story of German mechanics examining a captured Sherman reveals fundamental truths about industrial warfare that remain relevant decades after the conflict ended. Technical excellence in individual weapon systems matters far less than reliable production of adequate systems in overwhelming quantities. Manufacturing philosophy determines production capacity as surely as factory floor space or workforce size. And automotive industry maturity, developed through decades of civilian production, translates directly into military manufacturing advantage when properly applied. The three mechanics who conducted the initial examination understood these principles by mid-1943. Their detailed reports documented American advantages with scientific precision, but understanding a problem and solving it represent fundamentally different challenges. German industry lacked the capacity to restructure production methods during wartime. American industry had spent decades developing production capabilities that, when mobilized for military purposes, proved strategically decisive. Weber, Richter, and Baumann had examined one tank among 49,000 produced. That single vehicle told the entire story of industrial warfare's mathematics. Every component revealed automotive thinking applied to military requirements. Every design choice prioritized production efficiency over technical sophistication. Every system reflected confidence that volume production could overcome individual vehicle limitations. The Sherman represented visible proof that American industry had weaponized production itself, creating strategic advantage through manufacturing velocity and operational reliability that no amount of German engineering excellence could counter. The captured tank at Kummersdorf was evidence that Germany had already lost the industrial war even as combat continued, and that American productive capacity could not be matched regardless of German technical skill or tactical proficiency. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.